Hi friends, welcome back to the channel, and today we will be solving couple of problems which were asked in GATE 2020. This is again from the topic of mechanics of material. So without much ado, let's get started. So here we have a bolted assembly where there is a steel bar attached to a steel channel. Now the steel channel is subjected to an eccentric load as shown over here. It's applied at a distance of 400 millimeter. It's applied a distance of 400 millimeter from the center of the assembly. Make sense? So you're asked to compute, or you're asked to find out what is the resultant shear load on bolt B. Bolt B is situated over here. So the first step is draw the free body diagram of the steel bar. For the steel bar to be in equilibrium, there are two forces acting on it. There are two effects of this force. So this force can make this whole steel bar move downward. If there are no restraints over there acting here, then this whole steel bar would have it will simply slide down in this direction, but that is not happening. Why is it prevented, or why is it not happening? Because these four bolts are offering a resistance in the upward direction. Similarly, the other effect of this particular force is to turn this whole steel bar in the clockwise direction. So that is also not happening. Again, then that resistance is provided by the four bolts. So the four bolts are applying a torque in this direction, in the counterclockwise direction, to make sure that the steel bar is not rotating. So this particular force has two effects. One is to make the steel bar slide down, and to make the steel bar rotate about this point O in the clockwise direction. So that's it. So the physics is told in words. Now let's see how we can convert the same into a free body diagram. So this is how the free body diagram of the road along will look like. For the time being, assume that there is no this thing over here, and it is just simply the road, steel road I'm talking about. Then at the interfaces, at the bolt steel road interfaces, I have introduced some extra forces. So the red one, capital V, acting on the four bolts, will resist this 10 kilonewton downward force. Okay, so these four V's together will prevent the downward sliding of the road. And now, in addition to that, you can see some VT I have drawn. VT is the shear stress. Again, it is the shear stress acting on the bolts, but look at the figure carefully, and you can see VT is orthogonal to these lines here. These lines are connecting the bolts, diagonally opposite bolts. This line is connecting the diagonally opposite bolts. So now VT is perpendicular to that. Now what does VT do? If you look at these two forces, they form a couple in the counterclockwise direction. Similarly, these two forces, again, they form a couple, and then in the clockwise direction, in the counterclockwise direction. So that it means all these four VTs are preventing the rotation of the road in the clockwise direction. Make sense? Now, from equilibrium equations, we can write 4V is equal to 10 kilonewton. Why is it? It comes from the fact that when you take summation of forces in the y direction equal to 0, you arrive at this. So V is known to us. Now let's see take the moment balance. Moment balance is also fairly easy, because we have here four VTs. We have here four VTs. Then this root 2 times 50 millimeter, I'm converting that to meter. Root 250 millimeter is this distance. I can show you it in the figure. I'm referring to this distance because that is the moment caused by this force about this point. So we are summing the moments about this point, okay, to make things fairly clear. So the moment caused due to this force about this point is clockwise, while all the other four cause a moment about this point in the counterclockwise direction, and both should be the same for equilibrium. So that's what I have written over here in a mathematical form. From this, the only unknown is Vt. Vt amounts to something like this. The units are Newton. So now you have a look at closely at this figure. At the ball B, we have two forces acting. We have the V as well as the Vt. We can simply add them together because these two are vector quantities and they are not collinear. Had they been acting like this, then I can simply add them. But now these two are vectors, so we should give some kind of respect to these quantities and we should treat them vectorially, trying to write them as vector quantities. So at point B we have one force acting in this direction and then we have Vt acting in this direction. So V is fairly easy because we can write it as Vj cap because it is pointing in the positive y direction. If I introduce a coordinate system over here, like let's say x is this one and then y is in this direction, then V is fairly simple, fairly easy to write. But if you want to write Vt as a vector, then things get slightly different because now Vt is not along the unit vectors. Vt is slightly inclined, but we know the angle 45 degrees, so we know the vector decomposition rules and all that I'm not getting into. So Vt can be written like this: minus this quantity times the cos 45, then Vt plus sine 45 in the j direction. So this is the vector components or the what you get after decomposing this into a vector. I forgot to put a vector symbol over here. So this is the two vectors acting at this point B. Now you can simply add these two vectors. Once you add these two vectors, you will get this. Then the magnitude of this any vector ai cap plus bj cap, magnitude of that vector is root of a square plus b square. So that's it. You get the answer, and they are asking you what is the shear load on the bolt in terms of kilonewton. So your answer will be 17 kilonewton. Makes sense. So the key takeaway is that always treat this kind of problems from a free body perspective. Think about the effects. What does the external force try to do on the structure? Then accordingly take the reactions offered by the bolts. Make sense? So let's move ahead and solve another problem which was again asked in GATE 2020. Going ahead, we have another very simple problem to deal here. Uh, See, here we have a barrier and we have water on both ends filled to different heights. The density is given, everything is given. They are asking us to find what is the maximum bending moment developed in the cantilever. So they are trying to model this barrier as a cantilever. A very good problem, I would say, because it just checks your ability to apply the concepts whatever you have learned to real life problems. So good problem, they're asking us to find what is the maximum bending moment that is coming in this thing so that you can accordingly size the barrier or find the thickness and all those things of the barrier. We can, that's a very good problem, I would say. So without much ado, let's get started. So what happens once you draw the free body diagram or the what you call, you can, when once you draw this thing as a cantilever, this will be the external loadings, this will be the external loading on the structure. So here we have water filled up to a height of 4 meter, so the force will vary like this. It vary like this because we all know the pressure as the height increases varies like this, rho gh. If you take a unit length here, if we take a unit length, let's say this is 1, then the force acting that in this region will be pressure times the width. Width is perpendicular to the plane of the paper, but in this case it is 1, it is given as 1, it is given as unity, so it is again rho gh. This is the Newton per meter. Take care of the units very carefully because the pressure is Newton per meter square, units is Newton per meter square. Once you divide, once you multiply with the width of the barrier, then you get rho gh, Newton per meter. we are good to go, because when we solve beam problems we are looking for that lateral loading acting per unit length of the beam. Now you got that, this is simply rho gh. Then this is varying like this as a triangle. Then you know what will be the maximum lateral load acting per unit length. It will be rho gh. Rho is 1000, g is 10, and height is 4. So this magnitude of this quantity will be this much, and similarly magnitude of this quantity on the right hand side will be this much, because the height is just 1 instead of 4 over here. Now the next thing is, the to compute the bending moment, we can work with statically equivalent loads as well. So we need to compute the statically equivalent load for these two loading profiles, which is also not very difficult. We know this varies as a triangle, so the equivalent load will be equal to the area of this loading profile, which is half times height times the base length. Similarly here, and it will be acting at a point which will be h by 3 from this point. It is closer to this area, makes sense, because the centroid of this area is more close to uh, this side, because we have more area over there. So it will be acting at a distance of 4 by 3 from this base point, and here the resultant force will be acting at a distance of 1 by 3. Apologies for my poor sketch, but this is how the resultant loading will look like. Now things are fairly easy, because you're asked to compute what is the maximum bending moment. For that, what you can simply do is, you can sum up moments about any section and compute how the moment varies. A little bit of consideration will show that the maximum bending moment will be acting at this section. So acting at this section, were at this section, because the momentum is bigger here for this force. Even though there is this one trying to oppose it, the maximum bending moment will be felt at this section. It's simply a plug and check business, or rest of the things. You sum up the moments about that point, you get the bending moment acting in that section, and that will amount to something like 105 kilonewton meter. So that's the answer. The key takeaway from this problem is how you can reduce real life problems to simple beams, and then how you can find the maximum bending moment and all those things acting at the section. It's a really good problem, I would say. So we solved relatively two simple problems in this video. Thanks for watching. I hope you guys enjoyed it.